Okay, so hi everyone and welcome to another weekly seminar. Today we have one of our own, Sebastian Kiehlmann. So a few things about Sebastian for those of you who don't know him. So Sebastian received his diploma in physics at the University of Göttingen in Germany. And then he moved to the Max Planck Institute for Radio Astronomy in Bonn at the group of Anton Census, where he did his PhD, and he received his PhD from the University of Cologne. And then he moved to the Aalto University in Finland for a short period of time in 2015. Then he became a staff researcher at the Owens Valley Radio Observatory in Caltech. And then I guess he liked the good weather there. And then he decided to move back to Europe. And he's been with us at the University of Crete and the Institute of Astrophysics since 2019. And so he's working on active galactic nuclei and his jets and radio astronomy in general. And today he's going to talk to us about a very exciting binary black hole candidate system. So Sebastian, thanks, and the floor is yours.
Thank you, John, for the introduction. Absolutely, sun and palm trees should be criteria to select the next position, if possible, if you have the choice.
I'm with you. I'm with you.
So thanks everyone for joining in. So I want to talk about the Blazar Parks 2131-021, the unanticipated phenomenology that we discovered in this source when you looked at the radio data, and why we think that this source is a unique supermassive black hole binary candidate. This talk is completely based on this paper of the same title that we published about 1.5 months ago. And this was a major effort by the three main authors, which were Sandra O'Neill, a undergrad student at Caltech, myself working here at the Institute, and Tony Reedhead, an emeritus professor at Caltech, but also a very known face here at the Institute. And many of our collaborators who had a substantial impact on the data provided and the analysis and modeling. So this paper was a highly collaborative effort. And I just want to point out to the students in the audience that I think this is a very good example to pick up the chance, if you can, to get your hands dirty on some data analysis and do research early on, because as in Sandra's case, something really fantastic can come out of it. So this paper was published in AppJ Letters and accompanied by a series of press releases, because we thought this is really a very interesting result that we got here. So let's dive in, and I will start with a brief synopsis of this talk and this paper. So we looked at a radio light curve covering 45 years, which on its own is quite amazing, of this particular source. And we discovered that we have two epochs, one here, which show a strong sinusoidal variation, straddling a period of about 20 years where there's no sign of this sinusoidal variation. We convinced ourselves that this is truly a periodicity and not a random effect of an accidental effect of random fluctuations. So we think that this is a periodicity detected at 4.6 sigma significance level. And we concluded that the most appropriate model, or basically the simplest model to explain what we see here in this light curve, is a supermassive black hole binary. And in the following 40 minutes, I will go through the analysis and the conclusions we drew from it. But before I jump right into this paper, I want to give a brief introduction, because probably not everyone is familiar with blazars, and I want to briefly introduce what blazars are and what we know or knew before this paper about periodic variability in such objects. So active galactic nuclei are supermassive black holes at the center of a galaxy, and those supermassive black holes accrete material. Typically, the accretion disk is extremely bright and typically outshines the host galaxy. So fascinating objects, certainly. A fraction of those are even more interesting, at least to me, and those are the ones which emit jets. And those are called radio loud AGN, because the typical AGN non-jetted do not emit radio emission, but the jets do. If we see such a system as we did in the beginning of this animation, where you can see both sides of the jet at large viewing angle, we call this a radio galaxy. And when the jet is pointing almost towards us, as it is at the end of the simulation animation, as it is right now, we call those objects blazars. Blazars are interesting because the jets are moving at highly relativistic speeds, so very close to the speed of light. And when this motion is coming towards us, we're affected by relativistic effects. For instance, the emission is strongly boosted, which makes those appear much brighter and appear variable on timescales much shorter than intrinsically is the case. So blazars emit electromagnetic radiation throughout the entire spectrum, from radio to TeV gamma rays. They might also be the origin of neutrinos and cosmic rays, but that's certainly a quite recent topic and highly under debate. The emission, the electromagnetic emission, is strongly variable on timescales from minutes to years, depending on the part of the spectrum that we look at. So here we look at one of the radio light curves of one of the blazars that's studied a lot in the literature. So it's one of the archetypical blazars, showing strong flaring activity at random times. And typically this type of variability can be modeled very well with a red noise process, so stochastic variability. And this will be of high importance in this later in this talk. So despite the fact that the flaring activity can be described with a stochastic process, there have been claims of detected periodicity or quasi-periodic oscillations, so oscillations over a limited amount of time, in blazars throughout the spectrum from radio up to gamma rays. However, often the statistical significance of those results can be challenged. And there are even papers which state there's a periodicity without even testing what the significance is. So I want to give two brief examples. Covino et al. 2019 tested 10 blazars where quasi-periodic oscillations have been claimed, and they showed in this paper that all of that is completely consistent with red noise. So whatever has been detected as periodicity is just a spurious occurrence of a period of something that looks like periodic oscillation, but is not. A second example is that of Graham et al., who published two papers in 2015. One in which they detected 111 candidates out of a large sample of quasars, for which they reported likely quasi-periodic oscillations, and a Nature paper about this source where they claim this is the strongest case for a periodicity in the signal. However, 1 year later, Vaughan et al. Showed that again, this periodicity is completely consistent with red noise. And the main reason, the basic reason they give in this paper is, even if you do a significance analysis and find that you have a highly significant result, if you have a very large sample, there's of course a certain probability that you will find something that looks highly significant, because if your sample is large, that might just happen. If you don't take that into consideration, you will strongly overestimate the significance of your results. Despite those claims which can be challenged, there are, I think, two cases which are fairly well established. One is this source with a quite large separation between the two black holes of more than 7 parsecs and an orbital period of 3,000 years. So that, of course, means we can't measure any periodicity. This is all based on modeling of the radio images through via the eye. And the other case, OJ287, has a much smaller separation on less than parsec scales with a 9-year period. And this result is based both on optical data as well as radio data and radio via the eye observations. So those are the two cases that are, I would say, accepted as black hole, supermassive black hole binaries. But now let's dive into this object, Parks 2123-021, and what we discovered when we looked at the radio data. So this started with the radio monitoring program at the Owens Valley Radio Observatory with the nice 40-meter telescope. With this telescope and this program, which is running since 2007, we observed more than 1,800 sources, mostly blazars, but also some other types of objects. And we observe those sources 1 to 2 times per week. A part of those sources, the light curves of quite large fraction of those sources were publicly available up to a year ago when we took them offline. And so it happened that these authors contacted us around 2020 or 2021, who were looking at one of the light curves of our sources, the one we're discussing here, and found this sinusoidal variation and claimed that they had found a quasi-periodic oscillation. So they sent us the draft of this paper and asked if we would be interested in joining the publication, since they were using the data that we provided. And we had quite intense discussion about this paper and weren't within our collaboration, and weren't fully convinced of the statistics, but also didn't have the time to really dive into this project at that point in time. So we kindly declined the offer to join them as co-authors and just told them to go ahead with the publication as they had planned it. But nevertheless, we were interested because it looks like surprising sinusoidal variation, and we wanted to know how does it look in the more recent data. And in this part of the plot, you can see this adds already a year, more than a year of data, and it still seems to follow this sinusoidal trend. So we had this on our shelf for quite a while because no one in our collaboration had the time to really work on it until summer of last year when Sandra O'Neill joined us for a 3-month summer project. And at that point, we did a literature search and also found the data from the Michigan radio monitoring program, which showed something that could look like a 4th cycle in this oscillation here. There are some deviations from that trend here, but then in this early part, there's no sign of the oscillation that we see here. So it looks like just another quasi-periodic oscillation and nothing that persistently holds up to the point where you actually fit those 4 cycles and extrapolate this back here. And interestingly, this cycle matches fairly well those 2 flares. So luckily, we discovered more data from Haystack Observatory, which revealed another big flare here, which seems to match this cycle quite well. And so if you fit this part of the data with the green line here, so just a simple sign fit, you can see that those 2 separate fits match in period and phase quite well. And at that point, we were really intrigued and wanted to dive in and really dig deep with the analysis and figure out if there is something in there or not. So let's look at the statistical analysis that we performed in this paper. So we started with the weighted wavelet Z transform. So what you can see here on the x-axis is the date, so time, and here period of the oscillation on the y-axis. And in this WWZ plot, so basically what the WWZ technique does, you have a wavelet of sinusoidal wavelet, which you run over time, and you can test different periods, and where the wavelet form matches the data well, you get a strong signal. So this is clearly the case here in the third epoch, where we have a quite consistent signal over a large period of time and a strong one. There are two other peaks up here and down here, which are an order of magnitude lower in signal strength than here. So what we did in the lower plot is at each time bin, we identify the strongest value, the highest value. So for instance, here it would be something around 150, and then divide all the other values along this time bin by this highest value. So we end up with the strongest part, that the strongest signal is highlighted in yellow as the number of 1, and everything else is scaled between 0 and 1. And now we can see more clearly that here we have some periodicity, which roughly has the same period as here in epoch 3. And there's something which with a much longer period in the second epoch. The second technique we applied is the Lomskaga Periodogram, so the generalized version. And basically you can think of the periodogram as an average of the WWZ over time. So here we analyze the 3 epochs separately. So this is just for epoch 1. You can see the power in the periodogram, which indicates how strong a periodic signal is in the data. And this is shown over period in days on a logarithmic scale. And the strongest signal we find in epoch 1 is here at a period of around 1700. I will talk about those lines at a later point in the talk. So in epoch 2, again, we find a strong peak at a longer period, as we did with the WWZ analysis. And most importantly, in epoch 3, we have a very strong signal here, very little noise at other periods. So this is really a strong sinusoidal signal. And the period matches that of epoch 1 very well. Now, both WWZ and the periodogram just give us information about the period, but there's no information about the phase. But that was one of the things that actually got us interested when we looked at the data, that both the period and phase seem to match. So to also get some information about the phase, the next step we did was use sign fits to the data. And this is giving all the sign fit parameter results. I'm just going to focus on the period first. So up here you can see the period of the found by the fit. Down here is the period by the WWZ analysis and the Lomskaga analysis in comparison. And you can see that within the uncertainties, those results are really consistent. Similarly for epoch 2 and for epoch 3. And we also find that epoch 3 and 1 are consistent within the uncertainties, both in period as well as in phase. So in fact, it is actually possible to also fit both those epochs with the same sign function, so with the same period and phase, though different amplitudes and mean flux and noise contribution. So at this point, we've used 3 different techniques to check if there is a periodic signal in the data, and all those different techniques point us basically say, yes, there is a periodicity, and they all give consistent results. And I might add that we didn't only apply those 3 techniques. We also really wanted to make sure that we're not making any mistakes, that we're not making any false claims. So in fact, we had 2 people independently run the WWZ analysis with their own implementations of the code. We had 2 people run the Lomskaga Periodogram analysis. And for the fits, we had 2 people use least square fitting, 1 person doing maximum likelihood analysis, where these results shown in the paper are based on, and 1 person running Bayesian modeling with the sign function of the data, just to check that different kinds of techniques give consistent results within the limitations of each technique. And I think that might be of interest, especially to students and younger researchers, because when you read a paper, it usually looks like very straightforward thing. You have your nice description of data, then do some amazing analysis and come to even more amazing conclusions. But usually that's not as straightforward when you really do this. So I wanted just to point this out, because none of those multitude of tests actually went into the paper. We just for simplicity, we focused on one result in each case, but we went through all those tests just to convince ourselves that we're on the right track. And in fact, at that point, we had convinced ourselves that there is a periodicity in the paper. But of course, the next step is to estimate if this is a significant detection, in the sense that, as I told you in the introduction, blazars typically show strong flaring activity, which can be described with a stochastic process. So what we need to test is whether there's a true intrinsic periodicity in that source, or whether what we see is just an artifact, something that can happen sporadically in any realization of a red noise process. So to account for that, I will dive a bit deeper into how we actually did this for 2 reasons. On the one hand, I personally spent quite a long time, a lot of effort into this part of the paper. So it's my personal interest to convey that information to you. But the second and probably more important one is that we're fairly convinced that we provide a new method in this paper. At least we hadn't found this procedure in the literature, but there are lots of cases in the literature where the statistical tools have not been applied correctly. And that certainly is a very critical thing. So for instance, we found at least 1 paper where they used false alarm probabilities to estimate the significance. Now, the problem with that is the concept of false alarm probability is completely based on the assumption that you have white noise in combination with the periodic signal. And as I said, in blazars, we typically have a red noise process. So highly correlated noise, which means that the assumption of white noise doesn't make any sense here, which means that this technique cannot be used. So it's always very important with using any type of statistical tool to know the assumptions it's based on, to know its limitations and the conditions under which this technique can be applied. And when those are not met, one is not allowed to use this method. So how did we approach this problem, considering that we have a red noise process probably underlying the periodicity? So our null hypothesis is that the entire variability that we see in this source is coming out of a red noise process. So it's purely stochastic. There's no intrinsic periodicity here. It's just an artifact, so a sporadic event that can occur in specific realizations of this process. So that's our null hypothesis. So to test this, we simulate light curves that have the same statistical properties as our original data, meaning that it has the same power spectral density, which basically explains how strongly variable a source is on different timescales. And the second property is the probability density function of the light curve, which is just the distribution of flux density data points. So we have this algorithm which can produce simulated light curves that reconstruct both the PSD and the PDF of the original data. And here, as an example, I'm showing you 4 light curves. One is the original data, and the other 3 are simulations. And I'm not telling you which ones are simulations. And this is not for this source. This is a different source for which we did this. But I'm just showing this as an example to hopefully convince you that we are really doing a good job in simulating data that has the same statistical properties based on the red noise assumption. So we have all those simulations based on our null hypothesis. And if we can show that those simulations can never lead or rarely lead to periodicity as we find in the real data, then the implication, of course, is that the real data must have a periodic component. So as an example for epoch 1, here I'm showing the periodogram again. So the power of the periodogram versus period in log scale. So the black curve is the periodogram that we measured from the real data, giving our strongest peak here at this value. Now we have 10,000 simulations, and for each of those we calculate the periodogram. And at each frequency we can ask the question, well, how likely is it to have simulations that give us a power like we detected here or higher? So for instance, the 2 sigma line corresponding to roughly 5% will tell you that for instance, at this period, 95% of the simulations will have a power lower than this value, and the remaining 5% have a power higher than that. So for the case of the period that we detected here, this shows us that this period detection is more than a 2 sigma event. And this is basically the procedure that has been used in the literature when people correctly took into consideration the red noise hypothesis. However, and this is the new part that we contribute with our paper, we think that this is actually not, this is just the first step in the analysis. Because let's think about this like this. Let's assume that the light curve really is a result of a red noise process. And occasionally we detect a periodicity, which can just randomly happen as a coincidence. So there's no specific reason why this periodicity should have a period as we detected here. It could be at any period. One realization could have a period of 1,000 days, the next one 1,700 as we found it, and another one could have 2,000 days or whatever. So unless we know we expect a period at a specific, unless we expect a specific period, there's no reason that we should evaluate our significance at this specific period. So how do we deal with that? To correct for the fact that we should also take into consideration that a red noise process could produce periods, periodicities with arbitrary periods. So here I'm showing again peak power, and here is the peak period. The orange cross here marks the values that we estimated from the data. As in the previous plot, I'm showing the 1, 2, and 3 sigma lines here, and this red line corresponds to the significance that we estimated at the period that we detected. So let's call this the local significance. So at the period that we detected in the data. So this line, this was 2.3 sigma. So this line marks the 2.3 sigma threshold for all other periods. And now we have our 10,000 simulations. For each, we run we calculate the periodogram, identify the strongest peak, and then plot the period and power of the peak as a dot in this plot. So all the black dots you can see here mark the strongest peak in a periodogram of one realization of this red noise process that we're considering. And what we ask now is, how likely do we end up with a local 2.3 sigma event in all of those realizations at any arbitrary period? So what we basically just do is we count all the black dots above this red line. And this is what we think the right approach, and it has quite a drastic impact. So just as an example, based on epoch 1, when we evaluate the significance just at the period that we detected, we find 108 simulations that have a power as high or higher than we detected, which corresponds to this probability that the red noise process will produce a sporadic periodicity at that period, which corresponds to the 2.3 sigma event, as I shown before. But if we can consider that, well, if we take the look elsewhere effect into account and consider all the periods, then we find more than 1,400 realizations, which of course increases the probability to find such events in the data, in the red noise process realizations. And that just corresponds to a 1 sigma event. So the point is, if you evaluate this at just one period, you drastically overestimate the significance of your result. And if, for instance, 2 sigma would be the threshold where you claim, well, we consider this enough evidence to believe there's a periodicity, then this method that has usually been used in the literature would give you confidence to say we have a highly significant result, whereas actually it is not. Similarly with epoch 2, which is a less than 2 sigma event. However, for epoch 3, we have a quite significant detection of more than 3 sigma. Another thing I briefly want to point out here for epoch 3, since it is so significant, we ran 100,000 simulations, not just 10,000. And even in those 100,000 simulations, when we check for how often at the specific period that we detected the periodicity, how often we get a Lomskaga power higher than we detected, none of those realizations happen to show that. So the probability here is just an upper limit, and thus the significance is a lower limit. And similar here, this would be just a lower limit. So we could have gone further and produced more and more light curves, which just became unfeasible. And we thought that exceeding 3 sigma is good enough for our purposes. We're convinced that this is a significant event. I'm pointing this out because it's highly important to consider how many simulations you run. That was one of the points we stumbled upon when we read the Ren et al. Paper. So the original one discussing this source just based on the overall data. They were claiming a more than 5 sigma result. They were also running simulations, but just 10,000. But 5 sigma corresponds to an event 1 in more than 1.7 million. How do you test such a rare event with just 10,000 simulations? So it's not clear how they came to the conclusion that this is a 5 sigma event. So at this point, I've told you that, well, this is strongly significant, more than 3 sigma. This is not significant. So we're not going to discuss this apparent long-term period here, which you might see by eye as just 1.5 cycles. There are even less than 1.5 cycles. So this is not significant, but I've also told you that this is not significant. Which seems contradictory, but bear in mind that so far we've just considered this epoch on its own. So if you analyze just this part of data, then we come to the conclusion that this is not a significant periodicity. And I would say if I'd shown you this part, just this part on its own, no one would have ever picked it out by eye as a periodicity, because we have 3 strong flares and there's no good reason to consider this one cycle and this one another cycle. But what is really important, and what was the first thing where we started off, was the fact that if we look at those epochs separately, fit them separately, the fact that period and phase match so well. So let's take that into consideration when we do the significance analysis. So once again, epoch 3 is a highly significant, for astronomy. I think we can claim that 3 sigma is high. Physicists might object. Anyway, so we think that epoch 3 is a very significant detection of a periodicity. Epoch 1, analyzed on its own, is not. But when we ask the question, we have detected the periodicity with a period of around 1,700 days in epoch 3. How likely is it that a red noise process produces a periodicity in epoch 1 that has roughly the same period as we have in epoch 3? So now we have some prior knowledge given to us through the analysis of epoch 3. And when we do this test, this barely becomes a 2 sigma significant result. But now let's take both into consideration. So we ask the question, how likely is it that we detect a periodicity in epoch 3 and that epoch 1 has a periodicity that matches the period? So we multiply those 2 probabilities and end up here. And in the last step, we want to take into consideration the matching of the phase to within 20%, which adds another factor of 1/5 to the probability. And if we take all of that into account, the fact that we have a periodicity in epoch 3 and in epoch 1, a periodicity that matches fairly well in both period and phase, then a red noise process is very unlikely to produce what we detected. And we can claim that this is a more than 4 sigma significance result. Okay, I hope I've convinced you that what we detected is truly a periodicity and not just a random effect. So let's ask the question, what could be the origin? And there are different potential mechanisms, but we think that the simplest approach is that of a supermassive black hole binary. And the basic idea here is we have our supermassive black hole that emits the jet at a certain speed, very high speed, close to speed of light, at a small angle towards us, the observer. And when you have an emitting region moving at almost speed of light towards you, different relativistic effects kick in, which all end up in seeing a much brighter source than it would be in the co-moving frame. And this effect is called Doppler boosting. So the flux density that is emitted in the co-moving frame of the jet translates to a larger flux density in the observer's frame, increased by the Doppler factor D and by the power of 2 minus alpha. I'm not going into details here. The main point is that we see Doppler boosting, which increases the flux. And this Doppler factor depends on the velocity and the angle. The angle won't change, but the velocity will change, because if we have a supermassive black hole binary, both will move on an orbit, and the orbital motion of this black hole will modulate the velocity vector of the jet. And when we do the math, starting from Doppler boosting, doing Lorentz transformation from the co-moving from the black hole frame into the barycenter, and fill in the geometry of this model, we end up with this equation, which shows the fractional change in the flux density. And amazingly, it turns out that this truly has a sinusoidal form, which wasn't expected and wasn't clear in the first place. With an amplitude that depends on the velocity, the orbital velocity, the viewing angle as well as the inclination of the system towards us, the observer. And well, there are a lot of degeneracies in those parameters. So we didn't try to fit this model to the data that we have, but just filled in some typical numbers for blazars and could show that the fractional difference in flux densities that we see of 0.2, between 0.2 and 0.3, depending on the two epochs, that can be easily produced with typical parameters for blazars. So a supermassive black hole binary will naturally lead to a modulation of the signal in a sinusoidal form. So we don't believe that all of this is true, just the periodicity, just the periodic signal. Clearly, we have some smaller deviations here, we have stronger deviation here, and in this period, epoch 1, of course, it's much more clear with, for instance, this dip. So what we think is that we actually have two processes that we observe. One is the periodic signal, which originates in part of the jet being directly affected by the supermassive black hole, so most likely very close to the black hole. And then we have a second process, a non-periodic one, the typical intrinsic stochastic variability that we see in blazars, which could originate over a wider range of locations along the jet. And so we expect that we typically see a superposition of those two processes. In epoch 1, we would have a superposition of both in a high state. So we see lots of non-periodic variation and a strong periodic signal combined. In epoch 2, the periodic signal is not visible. So we probably don't have much emission from close to the supermassive black hole, but non-periodic variations coming from a larger region, probably further down the jet. And then in epoch 3, we probably have a superposition of a strong periodic signal with a much smaller non-periodic contribution than we see here in epoch 1. Now, why do we think, after going through all of that, that this source is a unique supermassive black hole binary candidate? Well, one thing is the period. So if we translate the period into rest frame, so redshift corrected, then this period comes down to about 2 years, which is significantly faster than that of OJ287, which I think was 9 years. And also the separation between those black holes is potentially smaller than that for OJ287, depending on the total mass of the system. And if the periodicity that we observe is really due to orbital motion of a supermassive black hole binary, then the implication would, of course, also be that we should that this system emits gravitational waves. And those could become detectable with pulsar timing arrays. So as it stands right now, based on nanograph estimations, there is no signal detected for this, this source. This gives us the just an upper limit. So here I'm showing the gravitational wave strain over the mass of the primary black hole. And this upper limit gives us a limit on the mass of the system. So if both black holes have the same mass, then we would get an upper limit of about 1 billion solar masses. If they differ by a factor of 10 in mass, the mass moves up. But we're in basically at the order of 1 billion solar masses would be an upper limit based on this non-detection. So currently it's not detected, but with future pulsar timing arrays, once SKA comes online, if the source has very large mass, it might become detectable. And that, of course, would be amazing to have a completely independent confirmation of our interpretation. But even if that is not the case, and even if it should turn out that this is not a supermassive black hole binary, it's still amazing to see, to detect this strong periodic signal in the data. And if it's not black hole binary, then, well, let's find out what else. At this point, we're convinced that supermassive black hole binary is the simplest approach to explain what we've seen here. And just to briefly sum up, so we've looked at the radio light curve of this particular source and found two epochs which show strong periodic signal straddling this period where this periodicity just fades away. But the amazing thing is that those two epochs match very well in phase and in period. And we went through a large set of statistical analysis to show that this is really a highly significant event, that this is not a random result of a red noise process, but that there must be a periodic contribution to the light curve. And that we think the origin could be a supermassive black hole binary. And in this paper, we showed that indeed a supermassive black hole binary naturally leads to a sinusoidal variation. There's more analysis in the paper, so if you're interested in this, pick up the paper, and otherwise I will gladly answer questions.
Thank you very much, Sebastian. I think people are clapping, so I'll do the sound effects. Okay, so are there questions for Sebastian? I certainly have some questions, but I will restrain myself for now. I see a lot of hands raised. So, okay, so let's start with Rafael. Rafael? Oh, we can't hear you, Rafael. Can you unmute yourself?
Now?
Yes, that's better.
Okay.
Thank you.
Okay, so Sebastian, thank you very much. That was really nice, and I understand a lot of things now. So my question is on the technical side of your work. You use the different ways to check about the strength of the signal, the Lomskaga and the wavelet, right? So I want to ask you, how do these tools, how different they are, and what's the caveat in Lomskaga, and why wavelets may be superior than the Lomskaga, and what did you see as you were experimented with the data? How do they compare?
Well, Lomskaga tries to detect periodicities in the data, as does weighted wavelet Z transform. The advantage over weighted wavelet Z transform is if you don't have a consistent periodicity in the data, because this technique takes into account changes over time. So if we look at the periodogram, this is the periodogram over the entire data. So still we see a strong signal here, which comes from those two epochs 1 and 3 when we analyze them separately. But this signal here, you can see this is has a value of 0.8, which indicates, so that the highest one would be 1 if you had a pure sinusoidal value. So you'd have a peak of height 1 and everything else would be 0.
So it's normalized. Okay.
Yes.
Okay.
So this tells us that this is really a very strong signal. And here, of course, it's not as strong, which makes sense, because we include all this data, which certainly doesn't have a periodicity at this period. So WWZ analysis has the advantage that you just test for periodicity locally by using the wavelet. So here you can really, in one analysis, show that, well, we have this periodicity of the period around 2000, it looks. Here, then it moves up to a longer period, which later we showed that this is not statistically significant at all. So it might just be a random realization of the red noise process. And then here again, we have a very strong and also quite persistent periodicity. So WWZ helps you to analyze data where sporadically or different types of periods occur that don't persist over time.
Okay, I see. Okay, I see. Thank you very much and very well done.
Okay, so thank you, Rafael. Nikki Lafes, Nick, okay, unmute yourself.
Okay, I will. Let me lower my hand. Sorry. Right. Sorry.
I did that for you.
Yes. Yeah. Good. Very nice presentation, Sebastian, and very interesting work. Could you please show the slide with the data, the flux density? You showed it many times, so that's right. Okay. Now, I definitely see periodicity in epoch 3. I tend to see periodicity. I'm tempted to say yes, it's there, but I'm wondering what happened in epoch 2. My knowledge is that binary motion is a very, very precise clock, very nice clock. So, and it's not as if the flux density increased by some non-periodic component and masked the periodicity. If anything, the flux density is somewhat on average lower than in epoch 1 and 3. So I don't really understand what happened during this period. So we have a binary and it's there and it keeps time, and yet something happened to this to the jet, and I don't know.
Fantastic question, which gives me an opportunity to throw in some more information from the paper, which I haven't had time to put it in, but I tried to give a brief answer nevertheless. So our interpretation is that, as I said fairly towards the end, we have two processes: the periodic modulation, which arises from close to the binary black hole, because there the gravitational effect is the strongest. And then we have a non-periodic intrinsic variation in the jet as we typically see it. So what we think is that the modulation here comes from close to the jet. So we have a component in the jet close to the supermassive black hole where the jet originates from. And that component is strongly affected by the Doppler boosting and this modulation due to the orbital motion. But we could imagine that in epoch 2, we still have the entire jet which is emitting as we typically see it from Blazar's non-periodic variability, but there's no component close to the black hole. So what we see here is not strongly, maybe not at all, affected by the orbital motion. And typically we see both, only that here a component close to the black hole is dominating. And this is consistent with what you pointed out, that here the flux density is actually lower than in those two cases. So we think that here we actually have a component close to the jet phase showing up, and that is affected by the periodicity. And as you said, exactly, it's a very consistent system, such a binary black hole, which is exactly why we think this is the most likely approach. Precession could also produce periodicities, but it's not, as far as I know, not expected to persist with a consistent period over such a long time. So exactly that persistency of the period over this long time, despite this epoch 2, is what convinced us that most likely supermassive black hole would be the reason for this periodicity. And just to quickly throw in one additional figure from our paper. So we actually think that we have further proof that those periodicities happen close to the supermassive black hole, because we have some VLBI data. So let me start with this one. So we have the 15 gigahertz light curve from Owens Valley, and the red ones are the fluxes estimated from VLBI observations. So the first thing to notice is that this tracks the periodicity as we see it in the single dish data quite well. Well, as good as we can tell from the fairly sparse data. But the nice thing is that with VLBI, the observations can be separated into different components, and we have specifically two components which follow this oscillation quite well, which is this one, which is the core. So the one that we think is the closest to the black hole. And the second one, which still shows a bit of this modulation, is this pink one, component 5. So the sum of core and number 5 is shown in this black curve. So you can see this neatly following the total flux density here. And the nice thing is that component 5, this here is showing the separation from the core. So component 5 is actually the one closest to the core. So those two components which seem to follow this modulation are the ones which are closest to the supermassive black hole.
Okay, thank you. That's really convincing. Thank you.
Okay, thank you, Nick. Dima is next.
Hi, Sebastian. Nice work, nice results. I was wondering, it looks like when you look at this light curve, that 2 or maybe 3 peaks, they are double, they have like M shape. You mentioned this for the second green peak, right? But it looks like the last but one has a similar profile, maybe the previous one too. Did you consider this possibility? What could it be? Why it's double?
We checked it. So what you're referring to is here we see this double peak most strongly. Then yes, here we have this, and here we have it again. There's nothing here, not clearly here. So what we did is we took the entire light curve where we see the periodicity and then folded it by the period. And it's not as consistent as it looks. So it's not that those peaks all match exactly. So we just think that it's probably nothing persistent, but just a result of the underlying red noise process that produces those flares.
Okay, thanks.
Thank you, Dima. Any other questions? Vincent is writing something, which I cannot see. Okay, so Vincent's question is, could precession of the orbital plane attenuate the flux in epoch 2? If such thing exists for supermassive binary black holes, e.g., preventing the jet to form a small angle with a line of sight.
So precession could certainly to periodicity in the light curve. As I said before, to my knowledge, it wouldn't be persistent over such a long time scale. But it's certainly possible that precession plays a role in this source, because I think we discussed it in a paper that this source has a quite unusually large opening angle. So typically blazars are more collimated than this one, and that could in principle be a result of precession. I don't think it exactly answers your question, but goes in the right direction, I hope.
Okay, so if I may follow up on this, and then Vasu, I will give you the floor. First of all, I'd like to say that people in pulsar timing arrays are actively looking for this system now in our data.
Well, give us the confirmation. That would be fantastic.
Oh, that would be fantastic. I agree. But on this topic of alternative models, I mean, it's quite, and to follow up on Nick's comment, I mean, it's clear that, I mean, you see some very evident periodicity in epoch 1 and epoch 3, which is not there in epoch 2. So isn't this, you know, periodicity that comes and goes, isn't this more consistent with something like a disk precession, for instance, where, you know, you can have a disk that wraps due to frame dragging, for instance, and then at some point it disrupts, and then you have some periodicity from that, and then that goes away, and then the periodicity goes away. Have you tried to fit such alternative models to see if they make sense?
So we didn't fit any models to the data. We just went into the general discussion of what models could be describing the data. And you're certainly right that disk precession would lead to, or could lead to periodic modulations of the light curve. But then again, in a case that you describe where it goes away for a while and then comes back, how likely would it be that those match in period? Well, in period could be, but matching within phase. So what finally convinced us that probably supermassive black hole binary is the most convincing, at least to us, is the persistency over the long period, and the fact that well, the fact that period and phase match so well, which is the persistency over such a long time. So we think that we certainly haven't shown that this has to be a supermassive black hole, by no means. That's why we say it's a candidate. So it would certainly be of interest to really go into modeling this with different approaches, but that just went beyond the scope of this paper. So if someone wants to go into the different mechanisms and test them, absolutely, that would be fantastic. It's just the persistency of the signal is what left us thinking that most likely supermassive black hole binary is at least the simplest mechanism you can imagine. And surprisingly, we didn't know that before. We were just assuming it could. But interestingly, it really exactly produces this sinusoidal modulation, as we show with the simple model.
Very clear. Thank you, Sebastian. So Vaso, final question.
Yes, Sebastian, what has this source been doing since the last data you showed in this light curve? Could you make a comment on that?
No, I haven't looked at the light curve since we wrote this paper. I have to check if I ran the data reduction for the latest data since we published it. Yeah, I think I should have more recent data by now.
Okay, I will follow up offline.
Do that.
Sorry, Carolina, go ahead. That was a short question by Vaso.
Sorry, just a very quick last question. Thanks, Sebastian. Very, very, very nice work and nice talk. So do you, since you mentioned OJ287, do you plan also to look into other wavelength light curve data? OJ287, for example, shows also this variability at other wavelengths. So maybe the case also here.
We looked at optical data in the paper and didn't find anything substantial there. but it's not nearly as well sampled as the radio data. So it's not entirely clear if we didn't detect anything because of data quality or if there truly is nothing.
How bright is it in the optical?
I think it's not a very bright source. I don't remember the magnitude, but it was not very bright.
Okay, thanks.
Okay, so thank you again, Sebastian, for the talk, and thanks everyone for the nice discussion. And until next time, so bye.
Bye, everybody.
Bye.
Bye.